So this is physics and calculus at the same time. Take 3 million. That's all you need to know. For the purpose of having easy to read numbers, I'm going to use 10 for gravity. So know that. So first we're going to look at a normal kinematic problem. We've got an orb of happiness being launched out of a cannon with an initial velocity of 10 meters per second. And that's a 37 degree above the horizontal. So that's a 3, 4, 5 triangle. So we know that from its starting height, it's falling off a cliff that is 3 meters high. We're trying to find how far it'll travel before landing in the x direction. So that's our unknown. So first we have to split this initial velocity into x and y components. So we have sine 37, 10, and cosine 37, 10. So in the y direction that'll be 8, and in the x direction I'm doing 6. Don't be scared. I'm not that smart. I'm not doing this math in my head. It's a 3, 4, 5 triangle times 2, so that's how I know. Right, so now all we have to do is write our x and y equations for acceleration. So a of y is negative 10. That's all we know, because gravity is 10 meters per second, and it's not being acted on. There's no other force acting on it in the y direction, so we know that's just the acceleration. Now, we're going to take the integral of this, which is calculus, obviously. It's this weird squiggly line. You probably know that. So the integral of acceleration is velocity in the y direction is equal to negative 10 times t, dt. That's important. That means this in terms of time. Plus c. And this c is our initial velocity in the y direction. So what we're going to plug in for c is negative 10t plus our 8 meters per second. And that is our velocity equation. Now we're going to take the integral of that one more time in terms of time. And we'll get negative 10t squared over 2. So the y is equal to negative 5 times time squared plus 8 times time plus c, where c it's its initial height. Now I could put in 3 for its initial height, and then for its final height plug in 0, but instead I'm just going to do 0 and negative 3 because it's physics and it should start at 0. It makes sense, so we'll just ignore that. So this is our height in terms of time. If you graph this out, it'll look kind of like the trajectory. It'll look like one of these, and the intercept will be like here or something. Okay. So no, it'll be at 0. So while this is what it looks like in terms of time, really, if we were changing distance, if there was an acceleration in the x direction, this could actually be stretched weirdly in this way. So if you're doing a problem that has an acceleration in both directions, you'd have to solve for time, or set this in terms of time, and then plug in x's where all the t's were, and then you'd have your actual trajectory equation. But this is fine for right now. You can still find everything you're looking for. It just doesn't look pretty. Okay, so now we're going to solve this for time. So what we're going to do is plug into our calculator. Sorry, ignore that. I'm doing weird math. I am definitely not in degrees. It doesn't matter, but still. So y equals negative 5 x squared plus 8x. I'd use t's to not confuse you, but you're calculus students, stop being babies. So that's what it looks like. What we're trying to find is when the change in height is equal to negative 3. So we have that second line there, and we're trying to find the intercept of those two. So I'll go to calculate the intersect, which is second, trace, and then 4. I think 4. Yeah. Don't really. Okay, so then you select your two curves, do the whole thing. And there, our intersect is at 1.91355, whatever. So that's our time. That's when it touches the ground. And this is the time bridge, which Mr. Landry probably taught you, which is what you do when you're solving a normal kinematic. Step 2, you gotta go to the x direction. So we have the acceleration in the x direction is equal to 0. The integral in terms of time is equal to velocity in the x direction, which is 0 plus c. And the c is the initial x velocity, so v of x equals 6. And then you take the integral one more time, and you get the x position is 6 times time. So to change an x, you just multiply 1.914 by 6, and then you get your answer, which is 11.484 meters. Hey, Mr. Landry. Okay, well, that was interesting. I got scared away by some jazz kids. No, we're playing clarinet. Wouldn't have been jazz. It was just instrumental. So I'm gonna do the second part here outside. It is humid and it's flooded everywhere, but it'll have to do. Cool. So again, gravity is equal to 10 because 9.8 is disgusting for small pieces of paper and recordings. Just deal with it. Right. So we have a rocket. Yeah. We have a rocket. Very happy rocket. And he is accelerating upwards at a changing rate. So what that means is the force coming out is increasing over time, and it can be said that it is equal to 600 times time plus 1,000. This means that initially it's got a force of 1,000, but then every second it increases by 600 newtons of force. Now this rocket weighs 100 kilograms, which means that's 1,000 newtons of force downwards from gravity. So initially its acceleration will be 0, which is very useful because it means I don't have to calculate it falling through the floor and other obnoxious things. But if the rocket was spending time winding up before now, it would be sitting on the ground at first. So you wouldn't be able to model it falling through the floor first before going upwards. You'd get an invalid, not really correct answer. So it's just starting from 0. That's a long-winded explanation. So let's just start like we start all of our force problems with one of these dealies. Yeah. So some of the forces. Here's our FBD. It's got force applied going up, force of gravity going down. So it's force applied minus force of gravity equals mass times acceleration. So we know all this except acceleration, so we can solve for it. So we have 600t plus 1,000 minus 1,000 equals 100 kilograms times our unknown acceleration. Divide the entire thing by 100. These thousands cancel out. Then we get acceleration equals 6t, which is very pretty for acceleration. So we're going to do just what we did last time. I should point out what we are solving for is after 5 seconds, what is the height of the rocket? So what that means is we don't care about the x direction at all. We just have to find the acceleration and then plug in 5 seconds for time and then we'll get the distance, because this will be in distance when we integrate it twice in terms of time. So first integration, we get 6t squared over 2, and that's v. So v equals 3t squared plus c, which is our initial y velocity. Because we don't have one, it starts from rest, we're just going to ignore it. So then we're going to integrate it again in terms of time. We'll get our y value is equal to 3t cubed over 3 plus c. And again, because its initial y value is 0, we'll ignore the c. So we have y is equal to t cubed. So we'll plug in our 5 seconds. Very happy. 5 seconds. 5 cubed is our y. So we've gone up 125 meters. Huzzah. Loud people. Right. Running out of paper. Gotta make this count. So, we're gonna do force of drag, which is directly related to how fast you're moving. The faster you're moving, the stronger the force of drag is. The slower you're moving, the less force of drag there is. If you're not moving at all, the force of drag is equal to 0, blah, blah, blah. It's usually negligible, but if you add a big parachute, it's not. So we have a car. It's a very terrible car. And the wheels aren't even connected. And it's on ice. Floating above ice. Magnets. It's magnets, guys. It's always magnets. That's what it is. So its initial velocity is 50 meters per second that way. And then it weighs 1 kilogram because it's magical. And then it's got a parachute attached to it, which is the car and parachute combo has a force of drag equal to negative 5v. So we can do our sum of forces in the x direction, which is equal to force of drag equals mass times acceleration. So negative 5v is equal to acceleration, because mass is 1. Okay. So acceleration can also be represented by dv over dt. That is change in velocity over time. So with this, we can actually do separation by parts a lot easier. What we're going to do is leave this negative 5 coefficient on this side to make it happy, but take the v and move it over here, and take the dt and move it over there. So we'll divide this side by v, and then we'll multiply both sides by dt. So we'll get dv over v is equal to negative 5 dt. That's how I'm supposed to do it. Okay, so if you add in your swoopy lines, you've already got your dv's and dt's, and you can integrate both sides without having to do weird stuff with computers and algorithms. So the integral of this is just a fact. You don't ever have to prove it. I don't think. I think you can do it with a u substitution, actually, but I'm not going to do it for you right now. We have ln of v, that's absolute value, on the interval from velocity initial to velocity final. Right, cool. So then that is equal to negative 5t on the interval of time initial to time final, or whatever time you're trying to go for. So this is ln v initial minus ln, no, sorry, it's final minus initial, ln v final minus ln v initial is equal to, if t is at first equal to 0, because time equals 0, it's physics, come on, get with it, we just have negative 5t. Alright, so thing with natural logs is you've got that rule where you can go like this. If you have one minus another, you can put the one on top of the other. Woo, is equal to negative 5t. So solving for velocity. We can plug in, we know what our VO is, but what we have to do is isolate V first. So you're going to go like, add a C. No, I don't need to do that. I'm sorry if this is confusing to you, deal with it. It's confusing to me because I learned it in 2 weeks, but it's a lot of fun when you know how to do it. Okay, so if you didn't have Mr. Dang, you'd probably call it something else. I'm snailing this. So what this is saying is e to the negative 5t is equal to VF over VO. Or just V, sorry. I don't know why I've been carrying F over, because it's a function. So now we have V alone. We multiply both sides by VO, which is actually equal to 50. So we have velocity is equal to 50 times e to the negative 5t. Boom. Right. Airplane number 2. Perks of living in Houston, guys. Right, gotta take the integral one more time. Don't know what I'm doing. So now, go up here. V equals 50 e times negative 5t. Take the integral of both sides. So what you gotta do is you have x equals 50 e to the negative 5t divided by negative 5. Yeah. Plus c. This just makes it easier to read in the equation at the end. Yeah. So we've got x is equal to negative 10 e to the negative 5t plus c. And we want x initial to be equal to 0, right? So what we gotta do is plug in 0 for x and solve for what t is, but I'm just gonna do that on the calculator using a graph. You got negative 10 e to the negative 5t plus some unknown number. So you have our graph. This is what its location looks like. Let me see if I can get this to look prettier for you guys. So it's initial. Hold on. We'll find the value at 0. It's equal to negative 10. So you just add 10 to it. X equals negative 10 e to the negative 5t plus 10. So that's our equation. Mr. Trout is speaking. He's retiring this year. You don't know who he is. Well, maybe you do, because you were a freshman in my senior year or something. This is what it looks like, more or less. So it gets up to about 10. And then at this point, the drag force is so much, it comes to basically a complete stop over the course of like a second. So I'm going to make this look like that. 0, 10, let's do 12. There. This is what that thing is doing over a second. Going really, really fast and then slowing down, eventually coming to a basic stop, basically a stop. Friction also would help with this in a normal situation, but really it looks like it's stopped at this point, but it's going just so small of an amount. Right, so that's our equation. If we wanted to find its location at any point in time, you'd just go value at x equals 0.25, and it has traveled 7 meters, 7.135 meters in that amount of time. That is drag forces. If this was just with laminar flow, which is like you've got your ball that is falling and the wind's going like this, round it nicely, and then it's going back on the other side normally. There are other kinds of flow where you actually use an equation. This is the force of drag equation that most people use for weird flow. Force of drag is equal to velocity squared. This is the velocity in relation to the air around it. So if you have wind going this way at 1 meter per second and you're going this way at 10 meters per second, the wind is actually traveling at 11 meters per second, so you'd use that for the V. Then this is your cross-sectional area of the figure that you're throwing at wind. And then you had the density of the fluid. So air is 1.225 kilograms per meters cubed, I think, something like that. And then you have coefficient of drag and maybe one other thing. That's what it looks like. Hey, sorry for the terrible quality of this recording, but I wanted to put a little thing at the end. So I want to say there's a 1/2. That's what I forgot on the formula. It's important. Not really, because you don't deal with anything. You don't even deal with drag in physics, but it's fun. So, you know, there's that. If you want to find terminal velocity, you just find when acceleration is equal to 0. That's about it. So I'm Drew Tollett. I'm a senior graduating 2015 at HSPVA. I'm in the vocal department. I'm in AP Calculus and AP Physics, and that's why I made this video, and I hope you enjoyed and hopefully learned a lot.